Alright, I'm going to get to work on these supplemental problems. The first thing that we have is this rectangle, and it's got a couple of charges in the corners. That's a pretty bad looking rectangle, but it'll do. This is value Q. This one is negative 2Q. This one down here is 2Q. And at the other corner is 3Q. I'm going to convert the centimeters right off the bat to meters, because that's how we like to do everything. This is 0.4 meters. This is 0.2 meters. And from that we can get that this diagonal is the square root of 0.2 meters. That's for future reference. We also know that Q is equal to 7 times 10 to the negative 6 coulombs. So the question is asking, what is the energy required to get these charges into this position from infinitely far away? And we're going to do this problem by using this equation. This is a general form. The Q1 and the Q2 don't refer to any of these. This is the general, where R is the distance between 1 and 2. That's what we're going to use. And we're going to use the superposition principle. So let's do it. This is going to be kind of long. We'll say U equals, well, you know what? Do I really need to write it all out? I don't think so. How about I'll just tell you instead of writing it all out. I multiply this charge by each of these in this equation, then I multiply this charge by the other two, since it's already paired with that one, and then I multiply this one with this one. And that'll be all the pairs of charges that we need to do. And of course incorporating the proper distances that are between each charge that I multiply. So the end result is really going to look like this. Equals K Q squared times, and this is, it'll be negative 2 over 0.4 plus 2 over 0.2, and this is after I factored out the KEQ squared, plus 3 over the square root of 0.2 plus negative 6 over 0.2 plus negative 4 over the square root of 0.2 plus 6 over 0.4. So I guess I was trying to save time, but I wrote it all out anyway. So all of that is going to basically come down to 8.99 times 10 to the 9th times 7 times 10 to the negative 6 squared. And all of these numbers added together come to a value of negative 12.24, rounded off. Alright? And that comes to a value of negative 5.39 joules. And it's joules because of what we're multiplying up here. I mean, I'm not going to go into the actual unit of Coulomb's constant, but we know that this equation gives us joules, and that's the equation that we're using with meters, coulombs, and this constant. So we know it's going to come out to be joules. And it's a relatively small number, not really a lot of energy there. And I'm not really sure how to explain the negative, except to say that that would probably mean that there actually has to be negative work done to keep this negative charge from being pulled in to these positive charges. That's my hypothesis. But I don't know. All I know is that I think that's the right answer, and it is negative. Okay. I'm not going to make another video. I'm just going to do it all at once here. I'll move on to this other problem. Once I erase the board. Okay. The other problem has that disc, but I'm going to draw it a little bit different. I'm going to draw it kind of like the book would draw it. Well, they would do a little bit of a better job than I did. But anyway, here's the center of it. And I believe this is the visualization they're going for. That's the axis. Goes right through the center. There's some point over here, P. The distance from the center is 2P is X. This distance is A. From the center all the way up is B. And then some point on the line from here all the way up to B is going to be some value R. That's what's going to be changing in this problem. The X is constant, and this will change. That distance is going to be the square root of x squared plus r squared, whatever r squared ends up being. So the other thing they tell us about this problem is that there's a uniform charge density. And this is dealing with area, so we're using sigma. And we know that sigma equals the charge over the area. And if we're going to be breaking this down into dq's, like we are, it also equals dq over dA. And we know that area is pi r squared, so dA is 2 pi r dr. So we can say that dq equals sigma 2 pi r dr. That's just the algebra. Alright. Well, I'm going to use the result from one of the examples in the book, and the only reason I feel good about doing that is because that's the way we did it on a similar problem in chapter 23 in class. So I don't feel bad about using the example, which says that the potential is equal to Coulomb's constant, big Q, over a squared plus x squared. Of course, this is not the a squared in our problem. It would actually be r squared for our purposes. But we can't use that because r is changing, so we're going to have to integrate. And we would do that by setting it up like this. It's going to be an integration, and we know our where we're integrating over. We're going to go from A all the way to B. So A to B. And we're going to be doing, instead of big Q, we're going to be using dq. But we already know what dq is in terms of r. Got that right there. So I'm just going to plug that right in. So Ke times sigma 2 pi r dr all over r squared plus x squared square root. Okay. So we have some constants that we can take out right off the bat. Coulomb's constant, sigma is a constant, 2 pi is a constant. Still integrating a to b of r dr over r squared plus x squared square root. So far so good. Now I'm not going to do the u substitution. I did a u substitution, but it'll almost be like using a table if I just write down the answer. So we know how to integrate it with a u substitution. But it comes to this result. Potential equals 2 Coulomb's constant sigma pi. I don't know why I'm changing the order, but those are what's out there. Multiplied by x squared plus r squared square root, that evaluated from A to B. I haven't evaluated yet, I've just done the integration. And so, all in all, the potential is going to equal this. That's the potential. And I guess just for the hell of it, that'll be volts. We know what we're looking for. We know it's going to be volts. I hope it's volts. But I believe that is it. That's the potential at point P in this situation.